Okay, so thank you for being back on time. We start now with a new topic. Luca Bottura from CERN is telling us about magnets, and this is the first of 3 lectures, correct? Please.
That's right. So thank you very much for the invitation. Thanks for the opportunity to give you 3 episodes about magnets, in particular magnets for the muon collider, which we will see at the end. Who knows about magnets here? Just lift your hand, just in case. You had to do with magnets. So great, nobody. Okay. No, just one. I see that. Hi. So all right. So the 3 episodes, I broke them up like this. So the first, you have the slides online already. So episode 1 is about superconductors, motivation, and then how do you design a superconducting magnet. I decided to focus mostly on superconducting magnets. I mean, normal conducting ones, they have their own theories, very important. I mean, most of the accelerators in the world are built using normal conducting magnets, resistive magnets, or permanent magnets. But we're going to talk about superconductivity, the 3 lecture, most of the time. Then in the second episode, I give you a bit of history, a bit of physics about the superconductors, and a bit of the machines that have been built with them. And then in the third one, I will use the muon collider as a case study to explain why they're important and why working on superconducting magnets for accelerators is important today. All right, so why superconductors? So motivation. And then superconducting magnet design, that's the hardest part, okay? So don't get worried. You get all the equations today. I'll do some of them on the blackboard just to break it, and you can follow with me. And but once that is over, it will be much easier. So that's a climb, right? And it's descent for the other 2 episodes. So why superconductivity anyhow? So for that, I use a graphic that is being prepared by one of the gurus of superconducting magnets, Martin Wilson from Rutherford Lab. He's seen it all, still alive, by the way, very active. So the idea is that you want to abolish Ohm's law. Okay, so that's what superconductors do for you. And in fact, having no power consumption, having high current density, very important, as you will see in a moment, makes that the ampere turns are cheap. And as you know, I guess, you know, physics you've had, if you flow a current in loops, then you generate a field. If you can flow a lot of current, you can generate a lot of field. The consequences is that you have lower running costs with respect to an electromagnet that has resistive losses, electrical consumption, energy savings. You can have high current density, very important, especially for the future, so that you make your devices much smaller, and you have higher magnetic fields accessible. So to give you already a feeling of what do I mean by higher, what I plot here is a current density versus field. And typically in electromagnets, we use current density in the range of few amps per square millimeter up to few, let's say 10 amp per square millimeter. That's the current density that goes around in the wires here. We're talking about 1, okay? And electromagnets, they are iron dominated. Iron saturates at about 2 Tesla. So essentially, that's the domain of fields that you can generate with electromagnets. You can push it, but you use a lot of electricity. Okay, so about a couple of Tesla, about 10 amp per square millimeter. Okay, just maximum. Now, if you take one of these superconducting materials that we'll talk about, niobium, titanium, that's what all accelerators have been built with. Current density you can flow in niobium. Is the mic on? Yes. Is of the order of 1,000 amp per square millimeters at fields of the order of 8 Tesla. Okay, so you can see there's 2 orders of magnitude of difference between the current density in copper and the current density in a superconductor. That's what makes economical generation of high magnetic fields feasible. And so again, to give you an impression, so if I plot current densities on the vertical axis versus field, so that's the 1 to 10 amp per square millimeter of copper. These are superconductors, all of them, okay? So again, 2 orders of magnitude above. We will come back to this plot, but it's essentially a collection of niobium titanium, niobium 13, and high temperature superconductors. And that's what it looks like. The same current gets carried by a bar of 100 millimeters, or by a 15 times 2 millimeter niobium titanium superconductor. They both carry 10 kiloamps, okay? That's again the size change, 2 orders of magnitude there. Okay, normal conducting versus superconducting magnets. I won't talk about normal conducting magnets after this. So normal conducting magnets, what happens is that magnetization ampere turns, so the iron magnetization is relatively cheap. You don't need much current to excite the iron. But the field is generated though by the iron, but is limited only by saturation, about 2 Tesla. You have low current density in the coils to limit the electric power consumption. They tend to be bulky and heavy, large mass of iron, which is, by the way, the cost driver. So you pay for the iron, not so much for the coils. That's what it looks like. That's the proton synchrotron at CERN, which is in operation since 1959. Okay. As I said, in superconducting magnets, superconducting ampere turns are cheap. The field is generated mostly by the coil, by the current that goes around the superconductor. You have high current density, it's compact, low mass, it requires efficient and reliable cryogenics, okay? So it doesn't come for free, you still pay for the cryogenics. And this is a picture of a superconducting dipole for the Tevatron, which is the first superconducting synchrotron, okay? That's the cross-section. We will dig in details in a moment. Okay, high current density, let's take the example of a dipole, okay? So as you can imagine, if you flow currents in a conductor bar, long in one direction, and the current comes back in the conductor bar in the other direction, you generate a field in the space between the two bars. And in particular, if you assume that you're sending current densities you've seen with titanium before, so hundreds of amperes per millimeter, so order of a million, sorry, there's a typo here. There's not a million mega ampere turns, it's 1 mega ampere turn. Okay, so a million ampere turns. You get a field, and at 375 amperes per square millimeter, you get about 8 Tesla, okay? That's essentially the LHC dipole, as we will see. If you had to do with copper, so we said there's 2 orders of magnitude of difference between the current densities. I only took 1 because it wouldn't fit in the slide otherwise. So if you take a tenth of the current density, you would generate the same field, but the cross-section would be spectacular, okay, as you can see. You would use a lot more material, you would use a lot more ampere turns because the cross-section becomes bigger. And instead of only have the cryogenic consumptions, you would have something like 6 megawatt per meter, okay? So imagine if you want to build an LHC out of that, you have a couple of nuclear power plants running the machine. So it's not feasible. And actually using this technology, the maximum field reaching dipoles is 16.9 Tesla, okay? And now you start having orders of magnitude already. Okay, so how do we design this magnet? Okay, now after the introduction, let's dig into details. So, normal conducting magnets, the way to design them is using Hopkinson's law, where you equate the magnetomotive force, F, to the reluctance of the magnetic circuit. Okay, the reluctance of a magnetic circuit, which has a very good iron here, is governed by the gap. If you equate the two, what you get is the field is proportional to the ampere turns, so the amount of current that goes through the coils, divided by the gap. Okay, so to generate a field of 1.25 Tesla in a gap of 100 millimeter, you need about 100 kiloamp turns, okay? So you don't push the current, as we said before, remember the mega amp turn. Superconducting magnets, instead, you typically design using Biot-Savart law. So that's the integral of the field generated by each current line in the coil. And so in the end, if you integrate it out for 2 lines, as an example, the field in the gap between the 2 current lines here is equal to the ratio of the ampere turns again, but in this case, there's no gap, there's the radial distance between the 2 current bars. And what you get is that if you have a radius here, 90 millimeter gap, again, it's about the LHC, and if you have a mega amp turn, you get 8.8 Tesla, okay? So it's a very simple exercise, and it tells you how to design the 2 magnets. Actually, field is one thing, but you want field homogeneity in accelerators. And the way to design for accelerators is usually to look at them in 2D, because accelerator, they tend to be long, and the magnet, they tend to be long and slender. So if you look into the aspect ratio of the aperture of an LHC magnet to the length of the LHC magnet, it's actually smaller than a spaghetto, okay? That's the aspect ratio that the aperture has. So the field in 2D, in an accelerator magnet, is usually described using a complex series expansion. It's very convenient. You build an analytic function, which is made by the sum of the y component of the field plus the imaginary unit times the x component of the field, which is equal to the series of the normal and skew components, the way they're called, times the complex variable. Okay, so z is complex variables in an xy plane. These are what we call also generalized gradients or harmonics. You may have heard about that. So the bn's are the normal components and the an's are the skew components. So this multiple expansion within the magnet aperture is essentially a series of field harmonics, right? So if you look into this z term, it's nothing else but the radius times the exponential of the imaginary angle. That's cosinus and sinus. So this is a series expansion in terms of cosinus and sinuses. Okay, so what do they mean? Okay, so here we go to the first blackboard exercise. So as I said, we built an analytic function which contains the y and x component of the field in 2D for an accelerator magnet, and then we equate it to a series expansion with coefficients. Let's try and get some values for the x coefficient, and let's see what happens with the field. So as a start, I will take all the coefficient equal to 0, but B1. Okay, so I say B1 different from 0. At a certain value, everything else is 0. Okay, that's easy because then I get Bx plus, By plus Ibx equal to the series of, there's only one term, B1 times Z power to the 0th. Okay, that's a constant, that's 1. So essentially, if I equate now the real and imaginary terms, very simple, By equal B1, Bx equals 0. Interesting. Okay, so that means that everywhere in space, I only have a B1, By component, which is homogeneous in space, always the same, which means that all the field lines are straight. Okay, that was easy enough to start. That's why I started with that. That's what we call a dipole. Okay, that's what makes the beam go around. Let's start with B2, different from 0. Right, and everything else is 0. Now we do the same thing. So By plus Ibx is equal to B2 times Z to the power 1. Z is actually X plus Iy. Okay? Now we expand. And what we have a real component, which is B2x, plus an imaginary component, which is I B2y. If we now equate real and imaginary parts, we get By equal to B2x and Bx equal to B2y. So it means that we have a field which has a linearly growing y component as we move along the x-axis, and an x component which is growing linearly as we move along the y-axis. Okay, so if I try to draw it, so By is growing along the axis x linearly, and there's no Bx. And Bx is growing linearly along the axis y, and there's no By. Okay? Now you can imagine the field lines, because in a point here, you have a field which is x plus y, okay, on the diagonal, so that, okay, let's use colors at this point. The field lines will go normal to x on the diagonal, normal to y towards the diagonal. Okay? What you see is that growing field, linear, is nothing quadruple. Right? Does it make sense? Okay, and indeed, so if you look at the shapes that you get, what you get with B1 is a homogeneous field. That's the dipole we saw before. B2 is a perfect gradient. That's the quadrupole we saw before. B3 is actually a sextuple. B4 is an octuple, and so on and so forth. That's very convenient. You can relate that to beam properties. Okay. Now the A's, I'll let you do it as an exercise. It's nothing else but turned. The dipole turned by 90 degrees, quadrupole turned by 45 degrees, and so on and so forth. They're skewed, and that's why they're called skew. All right, so how do we design then for an ideal dipole magnet? How do we get that B1 only, okay? And for this, okay, there's demonstrations, but I tell you the result. You can generate an ideal dipole, so homogeneous field, vertically oriented, only B1. If you have a current distribution that goes like the cosinus of the angle around a circle, okay? So you just have a maximum current, zero current, maximum negative, zero current, as you go around 360 degrees. And that gives you a B1 given by that, okay? We can do the same if you have two bars of positive and negative current density. You intersect them. The intersection is zero current, plus, minus, minus. So there's no current here. There's positive current density, negative current density. You get a perfect dipole field here in the intersection. The same you can do like with the circles with ellipses, okay? What I'm trying to do is slowly to bring you from this ideal mathematical distribution to something which has a cross section. Okay, that's how you wind the magnets. So you can find several solutions. None of them is really practical because it's not easy to wind coils of that shape. And by the way, if you instead of doing a cosinus theta current distribution or two ellipses, you go for cosinus 2 theta current distribution or 4 ellipses, can you tell me what the result is? Well, we want infinite time, so it's actually a quadruple, right? So cosinus 2 theta, that's the B2 we saw before, okay? 3 theta is a sextuple, 4 theta is an octuple. That's how you get the coil shapes, the ideal coil shapes that you want to reproduce. The same actually you can do instead of doing these ideal coil shapes by putting some current, certain shapes, like in this case, we call them sectors. So they're delimited by inside and outside circles and they cut down at a certain angle. You can also generate a B1 field here. Now, mind is not ideal, so it's not just B1. And I'll come back to that. Or you put plus minus current, you can generate a quadruple field, a B2 gradient, okay? And these are the expression. These are not the exact multiple magnets, but these are practical. You can build magnets with this cross-section. And in fact, this is the cut through the LAC dipoles. And as you see, you have here the sectors I was talking about. In fact, each one of these small blocks is what we call a superconducting cable. Many wires squashed together into a flat shape that can be wound easily. These are what we call the coil blocks. And as you see, they are spaced by what we call spacers so that you get more current density close to the midplane, no current density at the top. We are trying to cap the cosinus theta ideal current distribution. Now, I said it's not perfect. Indeed, if you take a sector magnet, what you get is that there's a main field, that's the expression for the B1, but there's also field errors. And the field errors are given by this expression. It's only interesting to know that first, there's only terms of order 3, 5, and so on, and there's no ANs. The reason is simple. There is symmetry here, which prevents skews. Skews means a rotation of the magnet. And because of the top-down and the right-left symmetry, you can also exclude the terms of order 2, 4, 6, and so on. Okay, so these are what is called allowed harmonics. So what we also see is that the field is proportional to the current density, J. That's the current that flows into each of the blocks here. And the coil width. Interesting. So in episode 3, we'll come back to that. Just remember, current density, coil width. Okay, so if you want the same field, if you have a higher current density, smaller width, less material. It will cost you less. Okay, that's an interesting piece of information. So as I said, these are the harmonics allowed by symmetry. And if you look into the allowed the harmonics produced by this configuration, what you can also see is that you still have a handle that the sinus of the pole position, that angle here, you can tweak as you want, okay? And if you take it equal to 60 degrees, that thing is 0 for n equal 3, which means that the harmonic B3 will be equal 0. Okay, so you cancel the sextuple. Okay, so you get a dipole which is not bad. In fact, that's what's been happening in going from Tevatron, Hera, RIC, the LHC. As you will see, there's an increased number of blocks and angles you can play with, because even the spacing of these blocks allows you to tweak some of those terms, higher order terms. So you can optimize the cross section to get what we call the geometric field quality, better approaching the ideal B1, the ideal dipole. Right, so far you've seen a lot of, theory. So actually, how do they look like, these wires? So, and we'll come back later on to how do you make them, so you understand what's inside. But essentially, they look like wires like this, where we have the filaments here, a multifilamentary structure that you can recognize, and that's the superconductor. Or that's a composite which contains the superconductor and residuals of the superconductor formation. And then you see a matrix invariably, okay, different colors, but usually there's a copper matrix, like in niobium titanium, niobium tritium, or there's a silver matrix, like bismuth compounds, HTS, or YBCO. And YBCO happens to be mostly in tapes, actually only tapes. While BISCO, you can get it in tapes or in wires. And similar to magnesium diboride, we'll see later what these materials are, which has a copper, monel, and nickel composite, okay? So these are the wires we build our magnets with. But before we build magnets, we make cable of that. So I already talked about this cable here, the flat cable, which is called Rutherford cable. So you can recognize all the wires here. They are squashed together to make it flat, nicely flexible. It's not the only form. You can have braids. You can have cables encased in a lot of aluminum. You can have cables which are internally cooled, or cabling conduits, the way they're called. Different cables for different applications. Okay, so this was the introduction on how you get to the cross sections and what these things are made of. Let's look at now at 3 distinct properties which are important for the operation, the successful operation of a magnet. First, margins and stability. So how do you make sure that the superconductor works as you intended? Second is the quench protection. What happens if you're no longer a superconductor? Third, forces and mechanics. You see why these are important. All right, so margin and stability. If you remember one of the first slides, there was a line, there was a critical current. They called it the critical current density of niobium titanium. Actually, that line is nothing else, so it's a part of a critical surface, because any superconductor will have to be cooled and will only remain superconducting if you're below a certain field. So the temperature limit under which you're superconducting is called the critical temperature. The field limit under which you're superconducting is called the critical field. And then the critical current is the current that is allowed to flow under conditions of field and temperature. So essentially, it's a surface here, where the vertical axis is the critical current density. One of the 2 horizontal axes is the field, the other is the temperature. So at any point in temperature and field, if you're below this surface, you're superconducting. If you're above the surface, you're normal conducting. Okay, so that defines the operating space of a superconductor. Now imagine that I slice that curve, okay? So I take a certain temperature, and then I slice the curve and I obtain the pink purple line here. Now, I have a certain critical current density, I call it JC. If I know the amount of superconductor I have, which I called A superconductor, ASC, then I can define a thing which is called the critical current. So the product of the JC, critical current density, times the cross section. And that I plot here, okay? That's a critical current. And the horizontal axis where I sliced was the field. Okay, so I get a line here. That's the purple line, which corresponds to this line here. Now, usually, so as I said, you have to be under this curve, you have to be in the pink plane, you have to be superconducting. So any operating point will have to be below this curve. Now, the magnet, when it operates, usually has an operating point here, let's say the Bohr field. And so let's pick values that are typical, 15 kiloamps and 5 Tesla. Okay, that's a typical design point for a superconducting magnet, orders of magnitude. Now, in reality, the coil will see a bit more field, okay, because there's not only B1, there's also harmonics. The field of the coil is a bit higher than the pure dipole field. So if you look in what we call the load line of the magnet, in the center of the magnet, you get the blue line, and that's the operating point where you want to be at. Actually, the coil sees a bit more. So for the same current, I'll be on the red line, okay, say 6 Tesla at the operating point. Now imagine that I ramp the current. What happens? I'll be moving up on this line until I reach the critical conditions. And then what they said is that above the critical conditions, you're no longer superconducting. So you start Joule heating. So there's a resistive heat. And this phenomenon is what we call a quench, exceeding the critical properties of the superconductor. That's when the magnet quenches. All right, so before we talk about how do we deal with the quench, let's look at how we compare the magnets, the material, sorry. So as you've seen before, all the wires and cables, they contain additional components. Okay, so when I talk about critical current density, I usually refer to the superconductor, but different superconducting wires come in different forms, and they may have different fractions of these materials, which can be copper, silver, astelloy, and so on in tapes. So how do we compare the various materials to know what is the actual engineering ability to carry current? And so instead of dividing by the cross-section of the superconductor, we can divide the critical current by the total area. And we call that the engineering critical current. So it's essentially the critical current density multiplied by the fraction of the superconductor to the total area, okay, this lambda. That's the engineering current density. That's a useful definition because we can plot the engineering current density versus field for various material. So essentially, as we did here for niobium titanium, we can do it comparing all the materials that are technically useful. And that's the same plot we saw at the beginning when we compared to copper. Now, comparing materials, okay, these are the orders of magnitude of the engineering current density versus field. We see that if we are looking for a range of hundreds of amp per square millimeter up to 1,000 amp per square millimeter, those are the values that I was quoting at the beginning. That's where a superconductor becomes effective, 2 orders of magnitude better than copper. We see that niobium titanium dies out once you reach the range of 8 to 10 Tesla. And essentially, that's the LHC. Okay, so the LHC is the end of the line of niobium titanium. You cannot go higher with field. There's another material which is being looked at, which is niobium 13. It's this curve here. If you intersect it with the range of 600 to 1,000, you see that you can generate fields of 14 to 16 Tesla. Okay? So again, this is the end of the line for niobium 13 for accelerator magnets. You can't go higher than that. Now, you also see that high temperature superconductor material, which are these bismuth compounds, bismuth, bisco, so it's copper oxide with bismuth and strontium, or YBCO, which is copper oxide with bismuth and barium. They can exceed by far the performance of what we call the low temperature superconductors, niobium titanium and niobium 13. And they can go above 20 Tesla. That's an interesting observation, and that explains to you why there's such an interest in high temperature superconductors, also for accelerator magnets. The question though, and that's how we will get to margins and stability, is can you actually reach these values in a magnet? So we know what JC is, we know what IC is, we know what IC relation to field is. Now, if we push and ramp the magnet all the way up to critical current, you will get a certain field. Can you get there? Okay, that's the question I want to look at now. And in fact, to look at that, I go back to the prehistory of superconducting magnets in the 60s, when people started building magnets, the first solenoids actually, for high energy physics, by the way. So it was built out of niobium zirconium. It looks like niobium titanium, is more or less the same type of class of material, and niobium 13. And what happened is that they quenched much below what people thought would be the critical current, the rated current. And the quench current increased gradually, quench after quench. Okay, so if you tried once, you will get here. If you let the magnet ramp down, cool down, ramp again, the magnet would get up here. If you do it again, it would get up here, get up here, get up here, and so on. So you get a phenomenon that was called training. Okay, so the magnet was getting better if you pushed it over and over. But they didn't quite reach what was expected to be the critical current. That's again the curve you see before. But all the quenches were actually limited to a current that was much below that. And so people started talking about degradation. Okay, so they thought, okay, we don't get to AC because the superconductor, something has gone wrong. Okay, in fact, this had to do with margin and stability. Okay, that was the 60s. You may say, well, 2025, we are much better than that. Sure. But what I plot here is training of the high luminosity LHC long quadrupoles in superfluid helium. It's a small plot, but you may recognize training curves. And you don't see that, but this current here is well below the critical current. Okay? So it's actually something which stays and has remained with the low temperature superconductor since the beginning. Now, why is that? Well, one reason is obviously operating margin. As you can imagine, if you are at the critical current, a small perturbation, which can be a tweaking current, which can be a fluctuating field, which can be more important, an energy input, may change the temperature, and that will bring the superconductor that is sitting happily just below the critical current above the critical current, and off you go, okay? So in this way, we have to define and use operating margin in the engineering of the magnets. So typically what we define is the ratio of the critical current to the operating current to the critical current, or the ratio of the critical current at the critical surface along the load line of the magnet to the operating current. Okay, so typically you want to be at 50% of critical current. Typically you won't get much higher than 80% along the load line. But what is most important is that you need a temperature margin. So how do I plot the temperature margin here? This was a cross-section, if you remember, of our magnet at 4.2 K, niobium titanium, what we sliced, the pink surface. You can do the same slice at different temperatures. And what happens is that those slices are coming down, right? Increase the temperature, lower the critical current. So there is a slice that will pass through the operating point. And that slice is at a certain temperature, which defines the temperature margin. So in this case, it was 5.7 K. And so the temperature margin from 4.2 to 5.7 is 1.5 K, okay? And that's the typical temperature margin that you need. Now, actually, temperature is not so much the temperature, it's the energy that matters. How tolerant are you to energy inputs? Because there's many things that can happen in a superconducting magnet, even in steady state. You can have small movements, you can have changing field, or things that we call flux jumps. So the frozen flux in the superconductor can actually flow. You generate energy. You can have thermal inputs. You can have nuclear events. You can have particle showers. You can have losses of beams. And that generates energy. And in fact, if you look at the energy range, this spectrum that comes from the various sources, what you see is that on different time scales, the various types of events can generate different types of energy densities. So it's convenient to measure them in millijoules per cc, because that's typically the energy margin of superconducting magnets. And what you see is that in the range of milliseconds, we're in the range of 10 to 100 millijoules per cc, okay? Keep these numbers in mind, 10 to 100 millijoules per cc of energy spectrum perturbation that enters into the magnet. Okay, so how do we know whether a magnet is stable then? Well, we need to make an energy balance between what gets in, the perturbation, and if it goes normal, the Joule heating. Okay, these are the sources of heat into the superconductor. At the same time, we have a heat reserve, that's the heat capacity, and we have cooling. You can conduct away, or the coolant can actually flow and take the heat away. Okay, so these are the sources and the pits. All right, I won't spend time. You can write down a very simple equation in 1D. The important thing is to retain just the heat capacity contribution, that's the accumulation, and the sources here. You won't deal with the conduction and the cooling. So typically what you get is that the temperature following an event, an energy deposition, increases in temperature, okay? It may actually go above the critical current because it will start heating, but if you have a good shunt, we said copper, silver, they're very good conductors, you may still have a chance to come down in temperature because there's cooling, and then eventually recover the superconducting state. Or if it's too much heat with respect to what you can carry away, have a thermal runaway, okay? So that's the effect of heating and cooling. So if the generation of heat is greater than the cooling, the transient goes to an unstable situation. The opposite, if the generation of heat is below the cooling, you go to a stable situation. Okay, so essentially, the analysis of stability to say if we have enough margin to operate the superconductor takes into account from a stable operating condition all the external energy input, various sources according to the spectrum, that there is a temperature increase, there may be a transition to normal state, you have to balance between generation and removal. If yes, you go to a quench, we called it a quench, if you remember, otherwise you go back to the stable operating condition. And the red line is what about stability analysis and design is about, okay? All right, so blackboard exercise number 2. Now, you don't remember that equation, but I bring it up just to use the terms. Okay, so I want to see how can I estimate the stability margin of a superconductor. So the equation at the bottom is nothing else but a 1D heat conduction, where I have a heat accumulation term, heat capacity, volumetric heat capacity times the rate of change of superconductor temperature. That's equal to the generation terms. So the external heat, which I called Q dot 3 prime, so watts per cubic meter from the external environment. That's the spectrum we were talking about. To be stable, and I want to neglect the conduction and the cooling. Okay, so I assume the thing is adiabatic, just to make things simple. Now, to end up in a stable situation, I need to end up at a temperature which is below the one of the critical current surface. And that means that I need to have no Joule heating, because if I had Joule heating, this temperature will always run away. There's no cooling, okay? So the stability margin can be evaluated by trying to integrate the balance between heat accumulation and the external heat source. Is that clear? Yes, no, yes, okay. So how do we integrate that? Very simple. Heat capacity is a function of temperature. We integrate it between the operating condition, the beginning, and the final temperature. And the final temperature, as I said, needs to be just below the critical surface, because if I'm above, I get Joule heating, the term on the right-hand side, and it will run away. But that temperature is when you get current sharing between the superconductor and the stabilizer. We call it current sharing temperature, TCS. So this is equal to the integral of the external source, say from 0 to infinity. Infinity means the end of the input, heat input, okay? So this is the heat, volumetric heat that goes into the superconductor, and the integral of the heat capacity in temperature is nothing else but the enthalpy. That's the enthalpy of the superconductor, or volumetric enthalpy. So this is the difference of the volumetric enthalpy at the current sharing temperature minus the enthalpy at the operating temperature. Okay? The difference in enthalpy is equal to what we call the stability margin or energy margin. So to know how much heat reserve I have to absorb, I only need to do the balance of the enthalpy between my operating condition and the current sharing. So how much is that? Okay, let me go quickly back to that. Okay, so that's what this says. That's the same thing here. Now, to get the enthalpy, we look into low temperature heat capacities first. That's this term, C. And what is interesting to note is that the heat capacity at low temperature goes down to very low values. Okay, that's a basic property of thermodynamics. I think you studied about that. So heat capacity is very low, and they actually drop as the cubic power of the temperature. We can integrate that and get the enthalpy. And so these are curves of enthalpy versus temperature for various materials. Okay, so we'll keep the slide here. Let's take one of the materials, just niobium titanium. In reality, it's a mix, but we take just one. They're all the same, actually. And assume that you have an operating point at 2K, the LHC. Assume that you have a temperature margin of 2K, more or less the LHC. What you see is that the difference in enthalpy between the operating point and the current sharing at the end, at the temperature margin level, is 3 millijoules per cc. Right? I told you, keep in mind the energy margins of the magnets. No, the energy spectrum of the magnets, 10 to 100 millijoules per cc. Okay? You see right away that, oops, we may have a problem here. We do the same at 4.2K. Okay, so we set the point at 4.2K. We take the same 2K energy temperature margin. What you see is because the heat capacity grows so quickly, that the energy margin is actually 10 times as much, 30 millijoules per cc. Okay? So what we see here is that the enthalpy reserve is of the order of the expected perturbation spectrum. So this is why stability is an issue in LTS. That's why you see training, even today. It's a physical limitation. Second is that do not subcool if you can avoid it. And in fact, even niobium 3T magnets, they train so much less at 4.2K than they do at 1.9. Now, let's do the same at 15K. Assume that you take a high temperature superconductor that can operate at higher temperatures. 2 Kelvin margin corresponds to about 100 millijoules per cc. Okay, this is also interesting because as you've seen, the envelope of this perturbation is typically 10 to 100. If you take larger margin, you end up in the 1,000 millijoules per cc because heat capacity is so high at this temperature. And so that shows that enthalpy reserve, because it increases so much, makes that stability is not an issue for HTS. Okay, high temperature superconductors are happily operating nearly to IC when they are at higher temperature. Okay, so stability recap, a sound design is such that the expected energy spectrum is lower than the stability margin, the stability reserve. Actually, you can do better than the simple adiabatic calculation because you actually have cooling, you have conduction, so it's not 2, it would be more than 2 millijoules per cc for the LHC. That's why it's working, by the way. Still, you have to design such that you're below the energy spectrum. To increase the stability, you want to increase the temperature margin, you have to increase the heat removal, you have to decrease the Joule heating, which means to have a parallel shunt in the material, which has low electrical conductance, copper, silver, and make best use of heat capacity. I showed you solid materials. Actually, helium, when it's cold, is the highest heat capacity of all the materials. That's why helium is so useful when you're cold. Right, let's go to the next step. Now, what happens if you're not stable and if you go the other side of the path? So now, to quench, there's an energy stored in the magnet, and that energy must go somewhere. Okay, let's evaluate the energy in the magnet. So the magnetic energy is a half Li square, it's B square over 2 mu naught. So if you take a process that happens uniformly in the magnet, so the dissipation of the energy in the magnet, and you take, okay, let's take a limit. Say copper melting temperature, 14K more or less. That corresponds to a maximum enthalpy reserve of about 5 billion joules per cubic meter. If you convert that into a magnetic energy, okay, that's B2 or B square over 2 mu naught, that would limit the maximum field that you can generate and still absorb all the magnetic energy and not destroy the coil to the order of 100 Tesla, okay? We don't have superconducting magnets at 100 Tesla, so in principle it's not a problem. But the problem is that the quench process does not necessarily happen uniformly distributed. And in fact, it may focus the energy in one spot, like it happened in one of the LHC magnets, where the magnetic energy was dissipated in a short to ground, where the energy was actually focused in an arc, and then it melts away kind of a fist size of copper, okay? So it's not very convenient. So we need to do something about that. So in fact, what we do typically is, you remember this sequence, if you have a quench, then you start having local heating, so you're no longer superconducting, you're resistive. The normal zone grows because you're heating the rest of the superconductor with a certain speed. You have a development of the voltage, so you see a voltage at the terminals. You detect the quench, because you obviously keep looking at the magnet, whether it's okay or not. And then you usually do a safety dump, okay? So you switch the power converter, maybe you switch a resistor in the circuit so that you discharge the energy. In fact, this is not an abnormal event. You need to design for quench, okay? So that's part of the normal life of a magnet. And that's the sequence seen into a diagram where you actually see all the phases, starting from a small blip. That blue thing that you see there is something that happened in the magnet. Actually, it was a mechanical movement. A wire moves, dissipates some of the energy, and then it suddenly goes a bit normal and tries to come back. So that blip goes down and up, down because of the polarity of the voltage. So don't worry about that. There is a voltage measurement, and then tries to recover, but it doesn't manage, and it runs away, okay? So that's where you get the propagation of the quench. At a certain moment, you put a threshold in the voltage, in voltage measurement, you detect the quench, you send a trigger to the circuit, which then fire heaters, by the way. When you have high current density, little time, you try to quench the whole magnet at once, and then you switch the power converter off, and then you get a dump. Okay, so you see it's a very complex phenomena with various time constants, and the discharge time is actually the sum of all the sequence of the things that are happening, right? And you need to try and keep that short. You don't have much time. We're talking about hundreds of milliseconds. Now, second exercise. So how do we know how much time we have, and how do we limit the maximum temperature that we can reach? And for that, so we start again with the same balance we had here. This time, though, the superconductor is quenched, and there's only Joule heat, right? The history of stability is finished. We are now generating heat, and we want to deal with that. So we take the same equation that we had before. This time we are only left with one term, which is the Joule heating. Now the Joule heating per unit volume, so this is a per unit volume equation, is the resistance per unit length times the square of the current divided by the cross section. Okay, that's fairly easy. So I call eta the resistivity, just to not to use rho density. Okay, eta is the resistivity divided by the cross section. I call it stabilizer because that's the stabilizer low resistivity material that is in parallel, the shunt we were talking about, times this current square. So this is the resistance per unit length times the current square is the power per unit length. And then I divide it by the cross section of the cable. Okay, so that's a per unit volume Joule heat. We equate the two. Now the only trick we do is that the stabilizer area, I say it's equal to the fraction of the stabilizer times the cross section. Okay, so just to have the cross section out. If I do that, what I get is that the Joule heat is equal to the resistivity divided by the fraction of the stabilizer times the current square divided by the cross-section square, okay? And that current square divided by the cross-section square is the current density square, okay? It's very convenient. Okay, so now let's equate these things. So I get heat accumulation is equal to resistivity divided by the fraction of the stabilizer times the square of the current density in the cable, right? And now I can try to integrate that thing. To integrate it, I do a trick. I divide the heat capacity by the resistivity, because the heat capacity is a temperature function. The resistivity is a temperature function. I integrate in temperature, and that's equal to the integral in time of the current density. Okay, current density is only a function of time. Now, this thing here is actually the reserve I have, the capital I have, that I spend because of the heat that goes in. So this depends on the circuit. This depends on the material. And I can compare the behavior of the circuit to the capacity I have in the capacity of absorbing that I have in the circuit, in the material. Okay, so that goes from the operating condition up to the maximum temperature that I want to allow. Let's call it T max. And this goes from 0 to infinity because that's a whole dump process till it finishes. Okay, so actually, this function here, which is that one, it's a function which we call Z, okay, material property. This function here is nothing else but the J square times the full time for the dump, okay? Like we called it the tau discharge before. And as I said, that Z is a material property. Okay, so let's forget about the fractions of material. It's just a very dumb exercise. What is important is that we can plot that Z for different material. So we get curves. If you get silver at very high purity, copper at normal purity, aluminum at very high purity, aluminum alloy with low purity, what you get is that you get different curves. And what you see from those curves is that if you set the maximum of a temperature, let's say 100 K, okay? If you get a point, say for copper, copper is a very common material, RR of 100, that's what we use in most of the magnets. Now, if we had used silver at high purity, we would have had much more ability to absorb that energy, and that would have resulted in a maximum temperature lower. If instead we used aluminum, then we would have reached a much higher temperature, okay, using that Z correspondence. Now, if we set the temperature to 100 and look at different materials, we see that you cannot protect a long dump if you don't have good resistivity, like a structural material that has very high resistivity, and you're much better off with a high purity material, okay? That's the integral of J squared dt. So when this integral is large, it's high current density or longer times. So this is convenient, this direction, and the direction towards zero temperature is convenient. Okay, so how to limit Tmax, the maximum temperature. So that relation that we just derived is an implicit relation between maximum temperature, the fractional stabilizer, the operating current density, and the total time it takes for the circuit to discharge. So to decrease the maximum temperature, you can reduce the operating current density. Okay, that's not very convenient. You need to discharge quickly. You can add stabilizer, increase the fractional stabilizer, and choose a material with a large Z. Okay, so protection is actually one of the difficulties in superconducting magnets, because the energy stored is a lot. You know, we have a very large field, the magnets are large. So instead of doing the exercise, I'll just show you the result of it. So actually the energy of a dipole, you can write it, believe me, like this expression. The expression is not important. What is important is that it grows with the square of the magnetic field, okay? Logical. And in fact, this is the stored energy in kilojoules per meter versus Bohr field for all the magnets that have been built or being designed, okay? So you see, indeed, there's a ratio, you know, this slope here is equal to, okay? So it's really growing with the B square. Now, I said we need to extract the energy quickly. Can we extract it outside with a resistor, or do we need to dump it inside, the heaters, if you remember? And for that, so you can compute the voltage that you would need to extract that energy as a function of the energy stored per unit length of the operating current, and they would result in a certain time constant, that time of discharge we were using before. You would like that to be small. If you plug in numbers, so typical current densities in copper, about 1,000 amp per square millimeter, that results in a temperature increase rate of 1,000 Kelvin per second, which means that you would reach 300K in a few hundreds of milliseconds. So that means that that tau is of the order of a few hundreds of milliseconds. And then with those values, you end up with voltages required to extract the energy of the order of a kilovolt per meter of magnet. Okay, let's pause a second. A kilovolt per meter of magnet. Take the LHC, there's 18 kilometers of magnets. Okay, a kilovolt per meter times 18 kilometers is a lot of volts. And that explains why it is not possible to protect accelerator magnets strings using an external dump. That's why we use heaters. That's why we need to make sure that the whole process homogeneously so that we dump the energy inside the coil. So recap on quench and protection. You need a good conducting material, and the effect of quench can be mitigated by adding stabilizer, reduce the current density, reduce the magnet inductance, okay? So if you look here, there's an operating current at the denominator that reduces the voltage. You want that current to be high as practical. And that's why we use cables and not single wires. That reduces the magnet inductance. All right, so a couple of minutes on force, and then we're done. So that's the last aspect. So you know that when you have an electric charge in a field moving, you have a force. Okay, so that's what accelerators are about. The same happens to a current, which is electrical charges in a wire in a magnetic field. So it's called a Laplace force with a force density J cross B. That means that the current that goes in a magnet generating a field generates a force on the wires that produce the field. If you take the example of a solenoid, that force, you can integrate the field profile in a solenoid is linear with the thickness. The field in an infinitely long solenoid is analytical. And what you get is that you have a force which corresponds to a pressure, which is equal to the magnetic pressure, B squared over 2 mu naught, which is the same story of the energy per unit volume. Interesting exercise to use those equations to see the orders of magnitude. So if you have 10 Tesla, as an example, you end up with 400 bar. That's a lot of pressure, okay? If a magnet is the size of tens of centimeters, 400 bar means you need a lot of structure because that's a lot of stress. If you take a dipole, okay, it's not just a pressure, there is a pressure, but the force is actually trying to push the coils one against the other. You know, again, the sector coil of the Tevatron, it's squashing the coils one against the other, trying to make it smaller, and trying to make the coil round. You know, remember the coils are long limbs, they want to become round, they open up. And in addition, in the ends, because of the way the ends are turning with respect to the field, the coil are also pulled. There's a force that tends to make the magnet longer. Now, how much is that force? Let's take the Fx and Fy. So these components here, you can do an analytical evaluation. A formula again, the important thing is that it goes with the square of the field. Okay, not surprisingly, magnetic pressure, B squared over 2 mu naught, the force goes like the square of the field. In fact, again, same plot, that's the horizontal force per unit length versus Bohr field. So as you see, they scale with a slope 2 in log-log scale, so it really is for the magnets built and designed like the square of the field. The force requires massive structures. Okay, we are talking about tens and hundreds up to 1,000 tons per meter. Okay, so these are massive forces. And the stress associated is also an issue for superconductor because many of these superconductors, especially a dye field, they're brittle. So if you push them, they crack like chalk. So it means that you have to mitigate that, and one way to mitigate that is to make the coil bigger, so decrease the current density, which in principle you don't want to do, more material, spend more. So in practice, the design of high field magnet is limited by mechanics. Okay, as much as superconductivity is important, that's the real engineering limit. Okay, so we went through. We managed to get to the end. Now I can give you a certificate, a superconducting magnet designer. And I wonder whether you have questions about this part. As I said, the other parts are more descriptive, a bit lighter in terms. If you do have questions, put them in the question session. I've seen there's a couple about HTS fluids and why are we sure that we can build a muon collider faster than FCC. Very interesting points. So we may want to discuss later on. Now to this, any questions? Yep. 1 year first, maybe.
You may have explained and I didn't catch it, but how come quench training works? Like, how come the magnet changes?
All right, no, very good, excellent. So what was not understood at that time is that that part of the spectrum was associated, as an example, with mechanics, and in particular with the fact that the windings, although they're well made, they may still have a porosity when you impregnate and pot the coils, or there may be locations where the wire is not properly supported. So what happened is that under the electromagnetic force, the magnet tries to expand, breathe, and then you may get cracks in the epoxy, you may get micro movements, you may get stick and slip, and then the wire actually generates some energy, quenches, but then it locks into a new position. And then the next time that it moves, then it will actually move somewhere else, where the force was not enough to crack the epoxy, so at a higher current. And then another time, and then another time. And then at a certain point, there's mechanisms that actually are stick and slip, they think slips, but then comes back, and then you keep training at the same place, and it doesn't change. That's one of the reasons, as an example. Now, a more tricky thing is that if you ramp the magnets in different ways, you can free current distributions, and that may give you better conditions at the next ramp. Okay, and so on. There was a question up there.
Hi, thank you for the talk. I'm sorry if I missed this, but I just had a question with superconducting magnets in general. Is like, I guess if Ohm's law doesn't apply, what actually causes, I guess, the current, or like, does that make sense? Because say you have a superconducting wire, which you put a potential difference between, what actually, I guess, causes the current to be the value it is to make the magnetic field? Does that?
I'm not sure I get it. So what is the question about?
Like, yeah, I mean, say I were to give you some superconducting wire and ask you to build me a magnet of this. What actually governs how much current goes into it if it's not Ohm's law? Or
okay, so I guess the question is about the design process. So if you, what we usually do is we start with take the LHC as an example. So the idea was to have the left tunnel, 27 kilometers. You have the beam. You want the energy, so you want the field. If you want a certain field and you want to use a certain material, niobium titanium, you end up with these equations to a certain set of current densities, coil cross section, and then you have to realize that in K. So essentially, you're doing the whole series of exercises we've done until you say, okay, this magnet is stable enough, the current is such that I can protect it, the mechanics is sound, and the electromagnetic force, you do the mechanical analysis, and then you set your operating parameter of the magnet based on, what is the margin, what is the material capability, what is the quench protection, what is the mechanical support, and so on. Does that respond, or maybe I didn't get the question?
like high school buildings, it's like, oh, I want this current, so I know the voltage and I know the resistance. So I guess in that, the plots you've been showing, what actually causes the plot? Like, is there any? I guess it's fine. I can look this up, and if I still have an issue, I'll come back to you. No.
You catch me at the coffee break.
Yeah, I invite you to ask questions of that kind, because I had the same question for a long time. I don't know if I could answer, but yeah, we can discuss those things that you might believe high school, not necessarily as high school, I can tell you. So think it's time to break here. Thank once more, Luca. And we are back at 3:30 with Hitoshi, who's joining us via Zoom.